Greetings, students. This is Mr. Allen, and today we're going to continue looking at integration. Today we're going to look at one of my favorite topics, which is U-sub, or what we know as integration by substitution. We have several objectives here. I'm going to try to move quickly through this so that we can get this down. I'm hoping to around 15 minutes. Change a variable, which is just a fancy way of saying use substitution. We want to be able to use the general power rule, which we'll talk about. I've got several examples. I'm not actually going to do all of them here. We're going to use the change of variable to evaluate definite integrals, and we want to be able to use the fact that a function is even or odd to help us integrate. So theorem 4.13, anti-differentiation of a composite function. This is kind of the foundation of our U-sub, and of course it's titled pattern recognition. So let me just kind of go ahead and jump to an example here. So I claim that if you look at this integral, it looks really hard, it looks complex, but what I claim is you should almost be able to just look at it and guess what the answer is. And when I say guess, maybe that's not the right way, maybe I should say educated guess. But here's what this is saying. If you recognize that you've got a composition of functions where the derivative of that composite function is also a product or a factor in that integrand, then the integral is very simple. In other words, so if we look here, this is, if you will, the g of x, and it's raised to the power 2. Well, this turns out to be the derivative of g of x. So we look at that x squared plus 1, that's g of x. Its derivative is 2x, so we can look at that as a composition of functions. And since it takes the form f of g of x, g prime of x, we can just use the pattern. So since we have this pattern, we can just go ahead and just think of this right here as x squared plus 1 to the second. So how do I integrate that? Well, you add 1 to the exponent of 2, which gives you 3. Now don't forget you got to divide by 3 as well. This is the answer. So what I guess I'm saying is, if we came back here, before I showed any of this work, I made a comment that I thought that some of you could just do this in your head. In fact, if this was a quiz or a test question, many of you wouldn't even need to show any work, and you'd be able to just jump right to this answer. So that's pattern recognition. Try using the chain rule to check that this derivative is indeed the integrand. In other words, if you do the derivative of this result, you should end up with the integrand itself, which it will work. So let's do another example, except this time we've got a slight little deviation here in that we're going to have a multiple that we're going to have to deal with. So again, I'm going to recognize that u is that 2x plus 1, similar to the last problem. Du is going to be 2x dx. Now here's the issue. I've got the dx and I've got the x, but notice there's this factor of 2. So what we're going to do is we're just going to move it over to the other side using division. So we could say that 1/2 du is equal to x dx. Now we can go ahead and do, and by the way, you could again do this using just mental math to figure out what the answer is. So it's going to be x squared plus 1 to the third over 3, but then just don't forget the 1/2 that we've added here. Okay, so the final answer then you could say is 1/6 x squared plus 1 to the 3 plus c. Now guys, I'm kind of doing mental math here, and I kind of hinted at this whole U-sub thing that we're going to do on the next slide, but this is kind of what's going on in my head. So this slide is the change of variable. Technically, this is the U-sub part. So this is where you would actually have to show some work. And again, some of the ones I do here, you're not going to really need to show any work, but nonetheless. And it should look like we're talking about the same thing, which we are. It's just now maybe we won't focus quite so much on the mental math. So for example, this one may not be as easy to do mental math with. Do you recognize what u would be? Well, u is this 2x minus 1. What would be the derivative of u? Well, du would be 2 dx. Now the problem with that is we have the dx part, but again we've got this 2. So what we're going to have to do is we're going to have to deal with this 1/2. So we're going to change this du to make it du over 2 equals dx. In other words, our original integral is going to now be transformed into this integral in terms of u, and this is still an indefinite integral. Of course, that divide by 2 could be pulled off to the front because that's our constant multiplier rule. Now we just use our power rule. So when I take what plus 1 plus 1/2 is going to give us the 3/2. So there's our new exponent. We have to then divide by that. We clean this up a little bit and we get our final answer, or not almost final answer, 1/3 u to the 3/2 plus c. But don't forget we need to change the u back to the original u value, which was 2x minus 1. This is our final answer. And again, if we wanted to check this, we could just differentiate it. Maybe I'll do that right now. So let's just do a check on this. And I will just go back real quick and recall that this was our original problem. Integral of the square root of 2x minus 1 dx. So I'm going to do the derivative of this. So I'm doing the derivative of 1/3 2x minus 1 to the 3/2 plus c. And of course, the derivative of c is 0, so I'm not too worried about that. I do need to do the chain rule here. So it's going to be 1/3 times 3/2 times 2x minus 1 to the 1/2 times, and now here's where I do the chain rule. The derivative of the inside is 2. Okay, and remember that c went to 0. Well, good news. Guess what happens to that 2 and that 2? Guess what happens to that 3 and that 3? So you are left with the square root, because that's what this exponent means, 2x minus 1. So that was our original integrand. So this does check out. So this is the correct answer. Okay, here are some guidelines for you to look at if you feel rusty on U-sub. I'm not going to read through all of these with you. This is the step that if I was taking a quiz or a test and I had time, I would make sure I don't forget to check it. But anyways. Okay, the generalized power rule is kind of, once you do enough of these U-subs, you just kind of start recognizing, wow, I can just think of that G function and think of the power rule with that. So for example, I've got, I think, 4 or 5 examples on these next 2 slides. I'm not going to go through all of them, but again, you could just look at this and say, okay, that's to the 4. So when I integrate that, that's going to take it to the 5th divided by 5, and you're good to go. And you should note that the derivative of 3x minus 1 is 3. So anyways, so this is the generalized power rule. In other words, you can think of this as just this 3x minus 1 is just x. And here's another example. Again, I'm not going to go through all these. I am going to do, not this one. The next one, though, I do want to talk about. So this one's kind of interesting because you've got a quotient. But on part E here, we're dealing with this integral of cosine squared x sine x dx. So you want to let u be the higher degree trig function here. So here we're talking about the cosine squared. So that's going to be your u. In this case, think of it as u squared. Now here's the one you got to be careful with here. What is the derivative of cosine? Well, it's negative sine. So that's where this negative, now if there's a negative here, notice there was no negative in the original integral, so that's why there's this extra negative here. So now we can just go ahead and use our generalized power rule. Cosine x quantity squared is going to be cosine x to the 3rd. Remember, we got to divide by 3 and plus c, and then don't forget that extra negative symbol there in the front. Okay, got 2 more things. Change a variable for definite integrals. I'm going to just do this. I'm going to show you this one just by example. First thing I'm going to do is I'm going to show you what you could do without using this theorem. Then I'm going to show you how this theorem would work. So I'm going to do a fairly simple integral. Here it is. And I'm going to show with way number 1, I'm just going to do u sub. So I'm going to say that u is x squared plus 1. Du would be 2x dx. I note that there was no extra 2 here, so I'm going to say that 1/2 du is equal to x dx. Okay, great. So I'm going to rewrite my integral. I'm going to say it's 1/2 the integral of u squared, oops, u to the 3rd, sorry, du. So that's my u sub. I'm going to go ahead and integrate. So this is going to be 1/2 times, and then I've got to divide by a fourth, because this is going to become u to the fourth. That's a u. We're not going to do the plus c, though, because we're doing definite integral. So this is 1/8 u to the fourth, and u here is x squared plus 1 to the fourth. So this is my, if you will, my antiderivative, right? This is my capital F. Now remember, when we integrate a definite, when we do a definite integral, we need to evaluate that. So this is going to be 1/8 of x squared plus 1 to the fourth, and we need to evaluate that from 0 to 1. In other words, this is going to be 1/8 parenthesis. Now I got to plug in 1. So 1 squared is 1, plus 1 is 2, raised to the fourth. I think that's 16. And then I've got to do the minus of the next part, so then that's going to be 0. So when I plug in 0, 0 squared plus 1 is 1. 1 to the fourth is 4. So that's going to give me, yeah, I think that's just going to give me 4. So then this is going to give me, I feel like I might have just screwed something up here. Am I okay? So 1 squared, that'd be 2 to the fourth, would be 16. Yeah, that's okay. And then 0. Oh, that's 1. Yeah, I just screwed that up. Sorry, guys. I heard a kind of a noise outside there. 1 to the fourth is just 1. So this is going to give me 1/8 times 15. So it looks like it's going to be 15/8. So the answer here is 15/8, or of course, if you want to write that as 1 7/8, that's fine too. Okay. So I didn't really do anything fancy there. I did actually what we just did on the previous slides with u sub, except I just had to evaluate it, the antiderivative from 0 to 1. Now I want to show you a different way. And again, I got to remember what my integral here is. So it is the integral from 0 to 1 of x, and then x squared plus 1 to the third dx. Okay, so here's what we're going to do. We're going to do pretty much the same thing. So that's going to be x squared plus 1. And I think we said that d was going to be, I think it was 1/2 equals x dx. Now here's the part that's different. I'm also going to change, let me get a different color here. I'm going to change these two variables here, the upper and lower limit of integration. So this is what I'm going to use to do that. This gives me the rule for u. U is x squared plus 1. Therefore, 0 is going to change to 0 squared plus 1, which is equal to 1. In other words, when I do this integral here in just a second, instead of having the lower integrand being 0, it's going to become 1. 1 is going to become 1 squared plus 1. So that's going to give me 2. Thus, my new integral is going to be as follows. 1/2 integral 1 to 2 of u to the third du. So not only have I changed the integrand in terms of u, but I'm also changing the upper and lower limits. So let's go ahead and integrate this. So this is going to be 1/2, and then I'm going to make this u to the 4, but then I'm going to divide by 4. Then we're going to evaluate this now. Instead of from 0 to 1, it's going to be from 1 to 2. So this is 1/8, and then it's going to be 2 to the fourth minus 1 to the fourth, which is 16, 115. So 15/8. So the reason I did this two different ways is I wanted to show you that, if I go back to the previous slide, there I did use sub, I did change a variable, but I didn't change the variable, the upper and lower limit. Gives me the result. I think that I like the second method better because once you get to here, I just think that this tends to be a little bit easier to deal with. If you look at that, you don't have to go back to that x squared plus 1. So that's the change of variable for definite integrals. Okay, last thing we need to talk about here are even and odd functions. And I just want to mention this because this is something I don't know that I did a great job of last year. If you have an even function, that means it's symmetric with the y-axis. In other words, the left side looks like the right side. So if I'm integrating from -a to a, -1 to 1, and there's a symmetry there, I really only need to integrate from 0 to a and then double it. Similarly, but different, if it's an odd function, that means the stuff kind of, if you will, in this case, above that means it's has symmetry with respect to the origin. That means that if there's this much area above the x-axis on this side, that means there has to be that much area below the x-axis. So if I'm integrating here from negative a to a in this case, that integral is just going to be 0. So this is all highlighted right here. So if you have an even function, you just double it, going from 0 to a. If you have an odd function going from negative a to a, that answer is going to be 0. And so we're going to look at one final example here, and you may not recognize that this is an even function. We could check it by plugging in negative x. So if we plug in negative x into f of x, you will see, by the way, this is f of x. When you plug in negative x for f of x, well, look what you get. You get the following. You get negative sine 3x to the third x, cosine x, minus sine x cosine x, which is equal to negative f of x. In other words, we can conclude that this is, oh, I said an even function, didn't I? This is an odd function. Sorry, this is going to be an odd function because this is a power, this is an odd power, this is an odd power, this is an odd power, and this is an odd power. So we're doing an odd power. So this integral is going to be 0. In other words, you don't even have to do the integral. The integral, I mean, it's just 0. If you want to work it out, you can, but you don't need to. It's going to be done. Another way you could think of this function, because I said it was an even, I'm sorry, is this. We could have factored out this cosine on both of those, right? We could have factored out this cosine here, and then you'd be left with sine to the third x plus sine x. Right, so this is clearly odd. This is clearly odd. This is clearly odd. So these are odd functions. So, anyways, I kind of didn't do a great job on that last example. I'm really sorry. I'm running out of time here on my prep period, so we'll end it there.